Assalamualaikum and a very good morning. How are you guys? We have how many participants? We have 36 participants. Not bad. But 41 of you have scanned the attendance. But the participant is 36. Maybe your internet is not. So for this week, for today, we're going to learn about gas chromatography. Have you uploaded in the beginning? Can you hear me?
Doctor, we cannot hear you.
That's why. Let me see. First. Okay, Assalamualaikum and a very good morning. Can you hear me now?
Yes, doctor.
Okay, sorry for that technical problem. All right, for this week or for today, we're going to learn about the gas chromatography. Have you all watched the videos that I have uploaded in the e-learning?
Yes.
Okay, what have you learned from the video? Can you tell me something?
Column.
Column, and then what else? I have uploaded two videos, right? The first one is about what? It's about the basic theory of gas chromatography, right?
Yes.
And then the second one is about column, right? What type of column that we use in the gas chromatography? What type of column do we have in the gas chromatography?
Pipe column, capillary column.
Pipe.
Yes. Pipe column and capillary column. Good. Right now, learn from the beginning of the gas chromatography. How to remove my Yeah. Can you guys see my video now? You see me? Oh, all right. Okay. So I'm gonna share the slide. Right. All right. So now we learn about the gas chromatography. Previously, we have learned about thin layer chromatography and then high performance liquid chromatography. And for today, we're going to learn about gas chromatography, right? Like the video before this, the principle of gas chromatography, right? And what is the difference between gas chromatography and another type of chromatography, right? Chromatography used for separation and analysis of volatile compounds. So now for gas chromatography, we are focusing on the volatile compounds. A chromatographic technique that uses a gas as the mobile phase, remember gas mobile phase that we have usually, is it the inert gas we use?
Yes.
Right,
Nitrogen,
good.
helium,
And
hydrogen gas.
yes. And then we compare which one is the best, right? In the video, they explain on how the performance of both all three gas. All right. The analytes are absorbed, okay, absorbed or dissolved in the stationary phase due to an equilibrium based on the vapor pressure and other additional interactive force, right? So now the analytes are either adsorbed, okay, or dissolved in the stationary phase inside the column. The mobile phase is in gas chromatography is referred to as the carrier gas, right? Instead of mobile phase, we call it as carrier gas because there is a little interaction between the analyte and the gas phase, right? So the gas solid chromatography or GSC use a solid stationary phase, and gas liquid chromatography GLC use a liquid stationary phase that is bonded or coated onto a solid support, right? So when we are using the GC, the first one is and then the sample is vaporized and injected onto the chromatographic column, and the sample is transported through the column by the flow of gases mobile phase. Now, you have seen in the video, right? So there's the column of the gas chromatography is very long, right? Need to be in coil, right? And then what happened? Being done? What is being you know what kind of process that are introduced to the column in the gas chromatography? We have the oven, right, to heat the column. Am I true? Why do we need an oven to heat up the column? Of a gas chromatography instrument, we have a carrier gas, right? Wait, and now Now we have a pen. Right. I want to annotate the screen, right? Right. So here we have the cylinder gas, right? That is the container for gas, right? And then in the container we have the carrier gas. You say that it's inner gas, right? And then we have with HPLC, we have the injector in. What is the thing that we're going to inject into the system? What is the thing we're going to inject into the system, into the gas chromatography? Is it the mobile phase? What is the thing that we're going to inject into this chromatography?
Sample.
Yeah. Yes, of course. We have to inject the sample. And in the video, you have seen the temperature that being introduced into the sample injector here. The oven, am I true?
Yes.
To heat, yes, thank you. Why we need to heat the sample that being introduced into the gas chromatography? Can anybody tell me?
To become volatile compound?
Yes, because we need it in the volatile form, right? Remember the GC, we analyze the volatile compound, right? So we need it volatile, we need to be in gaseous form, right? And then before the sample travel to the column, it need to be volatile first, right? Then it will travel inside the column, right? And then we have in every analytical instrument we have the detector, right? Give me one of the common detector that we have in gas chromatography. You have watched in the video. What? Start with
ID.
FID. What is FID? Oh, what happened to my pen? Flame ionization
detector.
Detector. All right. Thank you. All right. So now, GC process. Through the septum, the sample is vaporized and injected onto the chromatographic column. The sample is transported through the column by the flow of gases. Picture of the real GC set, right? Here we have the what kind of symbol is this? What kind of symbol is this? Right? Meaning that we have the heating. We have the heating coil inside the injector compartment. All right, and then we also have the auto sampler. So now, what kind of our sample should be in what kind of what form? Is it in right? For this one, it should be in liquid. Well, we also have GC that can analyze the solid sample, but it is in different type of sampler. So we need to prepare the sample, and we can put it as, for example, a strawberry. We can put inside the compartment, and then it will heat it and introduce into the column. We have that type of chromatography. We need to know what is the, for example, pesticide in the fruits. We put a strawberry inside the compartment, one strawberry inside there, and then the
a volatile organic compound that contained in the sample, right? All right, this is the carrier gas, okay, right? And we have the capillary column inside here, inside the oven, okay? And we have fan, okay? What is the function of the fan? We heat it and we put fan for what? You want the fan to keep the oven cool or what? Why we need fan inside the oven? That is the maybe an IQ question for you. Why you need fan there? And anybody? Come on, guys! You are engineer. Engineer 3.
To control uniform temperature.
Yes. To control or to ensure that we have a uniform temperature inside the oven. We have a homogeneous temperature, right? In all part of the. Thank you, Anis. Now, this is a column, okay? We have, several type of column. We have the carrier gas, we have the injector, right? The detector, all right? We have the oven here. Must be used. Choice of gas is dependent upon the type of detector. The system contains a molecular sieve to remove. When we have the gas cylinder from the from the factory, it is impossible that our gas is completely without any interference or impurities. It must be there some impurities inside the gas cylinder, such as the water or other impurities. So we need to have a molecular sieve, all right, to remove the water or impurities, all right. And then, so the why we need to remove all the water and impurities? This is also an IQ question for you. Why we need to remove all these things, water and impurities? Other than Anis, please. Boys, come. Answer the question. Why we need to remove the water and impurities? Come on. I have told you before this. Similar with the spectroscopy instrument. We need to filter a sample. Okay, Ifan. Why?
Maybe to avoid interference.
Okay, the first one is to avoid the interference in the chromatogram. Is your what you mean, Ifan? Right? And then
yes.
okay, thank you. Okay, then give me other answer. Why we need to remove the water impurities? Of course, you want to avoid the interference inside our result. Okay, inside our data, we need to remove, or we need to make sure that only the analyte is there, not the interference, right? In analysis, we need to remove, or we need to eliminate as much as we can the interference, right? And then another one is what? Why we need to remove water impurities? Anybody? Do we love our instruments?
Yes, it's expensive.
Yes, it's really expensive, right? The maintenance are also expensive. So now we need to avoid the clog or any damage inside our column, inside our injector, and every part of the instrument. We need to make it very clean, all right? We need to make sure that all the carrier gas or sample is really clean from the interference. Thank you. That is the purpose remove interference from the result and to avoid the clog or any damage in our instrument. So, okay, gas type. Carrier gas, nitrogen or helium. Inside the capillary column or packed column, the flow rate is 1 to 2 milliliter per minute. For packed column is 40 milliliter per minute. Okay, now, if you watch the video, in the video said that nowadays we only use what type of column?
Capillary.
Yes, because the packed column is no longer used. Refer to this. What? We still have to use packed column to analyze what? To separate the. Remember in the video? Okay. Anybody can give me the answer? When does we need to use the packed column? Watch the video again. Then answer me, okay? So the detector gas, we have hydrogen and air, okay? All right. The second one is the injector split or splitless sample injector. A hollow heated glass lined cylinder where the sample is introduced into the GC. A micro syringe is used to inject the sample through a rubber septum into a flash vaporizer pot at the head of the column. So this is how the okay, with a capillary column. Okay, after the injection, the sample forms a mixture of carrier gas, vaporized solvent, and vaporized of the sample pot is 50 degree higher than the what? What is B?
Boiling point.
Yes, boiling point of the least volatile component, meaning that we know already in our sample what kind of analyte that we have to analyze. So in our prelim study, we must ensure that what is the least volatile component inside our sample. Then we need to set the temperature 50 degree Celsius higher than the least volatile component. For example, we have in our sample, name me the hydrocarbons. We have, for example, CH4 and C what? C10. So how much is H if C is 10? What's the H if C is 10? Remember the formula Cn and Hn. How much? Come on, petroleum engineers. C10H.
Maybe
How much? Draw the structure. Okay, so 21. Is it true, 21? 22?
22.
Yes, why 21? 22, right? So the formula is C N H N plus O N and what? We need to double, right?
H2N plus 2.
All right. N plus 2.
H2N plus 2. 2N.
N plus 2.
2N plus 2.
2N plus
2.
2. Right, because at the end of the carbon chain we have another H, right? Right. That's why we have to plus 2. Okay. Right. So from CH4 and C10H22, which one is less volatile? Which one is less volatile? This one, CH4. CH4 less volatile than C10H22. This is only logic. Which one is less volatile?
CH4.
CH4 less volatile. This one, C10H22 is less volatile. Why? I said to you logic, because this one is heavier. We have 10C and 22H. It needs a lot of energy to make it volatile, right? Rather than, what kind of gas we call this? CH4. Methane. Am I true? Right? So C10, what is C10? If this is methane, what is C10? Decane, right? So decane is less volatile. Or somebody said that decane is more volatile than methane. You don't agree with me? Right, so come on, answer me. Which one is less volatile? With a confident answer. Which one is volatile? I would like to ask Nisrin Nabila, which one is less volatile between methane and decane?
I think methane.
Why? Why methane is less volatile? The basic, right? Remember your organic chemistry. Okay, Abdi Samad Dayib, you said decane. So why decane is less volatile than methane?
Because it needs a lot of energy to make it volatile.
Repeat my answer. All right. Okay. We have long chain 10C, right? Up to 10. To make it volatile for C that have 10C and rather than 1C, more easier. Of course, the methane, right? Because you need a lot of energy to make this long chain to be volatile, because it is naturally in form of what phase? Decane is naturally in what kind of phase?
Gas.
gas. In the normal temperature, is it gas? Can Google. Okay, now Google the boiling point of methane and boiling point of decane. Which one is higher? Give me the figure. What is the boiling point of methane and the boiling point of decane? Methane, negative 161.6. Right, meaning that it's at very low temperature, methane already volatile. So what about decay? 174. So it is in the form of what? The normal temperature.
Solid.
What phase? Solid. I don't see a solid decane yet, so it's a liquid, right? Okay, so meaning that in ours, if we know that both of the hydrocarbons inside our sample, so we know that decane have the higher boiling point, meaning that the decane is less volatile than others. So we need to set the temperature 50 degrees higher than the decane boiling point. So the decane boiling point is 174, right? We need to set the temperature. How much? What is the temperature that we need to set? Injector. If the decane boil at 174, so what is the temperature that we need to set at our injector?
Two hundred.
200. 174 plus 50. 224, right? At least 224 or higher. All right, you got a point. Okay. Right. Okay, the split injection, the simplest method, either if only a small number of components present, not for trace analysis. Injection port fitted with two valves. In the first, acting as septum approach, allowing a small flow of carrier gas from just below the septum, and a second taking carrier gas from the bottom of the injection port near the column inlet. In split mode, lower valve is used to adjust the ratio of carrier gas going to waste in the atmosphere compared to flow onto the column, and typical ratios 10:1 or 50:1 used so that only a small proportion of the sample is transferred onto the column. Okay, you understand the split injection? That it is ideal if only a small number of a small number of components present, not column. A small number of components are present and not for a trace analysis. Injection. What is trace analysis? Meaning that a really low this low concentration. So injection port is fitted with two valves. Okay, we have two valves. The first acting as a septum purge, allowing a small flow of carrier gas from just below the septum, and the second one is taking carrier gas from the bottom of the injection port near the column inlet. In the split mode, lower valve is used to adjust the ratio of the carrier gas going to waste in the atmosphere compared to flow onto the column. All right, and the typical ratio is 10:1 and 50:1. It used to so that only a small proportion of the sample is transferred onto the column. All right, split injection looks like. So this is the total flow, and then it is divided into two. The septum for the purge vent, and then also here, right? And then this is to the column, right? Okay, and then we have also the split vent, right? And this the carrier gas together with the analyte will go to the column, inside the column. Splitless injection suitable for samples containing trace compounds, all right, in low concentration, because necessary to transfer as much sample as we can, of course, right, as possible onto the column to increase the sensitivity. And the lower valve is closed at time of injection, and only a small septum purge flow is used. Injection takes place into heated zone over a period of 20 seconds, so that all sample is transferred to the column. After predetermined period, 40 to 60 seconds, the lower valve is open to purge the injection port and to prevent residual sample from causing tailing of the pit. Right? So in the splitless injection, we don't have the split vent, so we close here. Because our analyte in this, we know that our analyte in the sample is really low, right? Trace level meaning that we have a low concentration of the analyte, so that we close the split vent, okay, so that we make sure that as much of the sample will travel to the column. All right. So now you can differentiate between the split injection and splitless. Right. It is for split injection is only suitable for small number of compounds, meaning that not so much analyte inside the sample, and not for trace analysis. Not so much analyte meaning that not so much type of analyte, right? And not at the trace analysis meaning that not at low concentration, right? So we divide into two valves. The first acting as a septum purge, allowing small flow of carrier gas just below the septum, and the second is taking carrier gas from the bottom of lower valve is used to adjust the ratio of carrier gas going to waste in the atmosphere, all right, compared to the flow onto the column, right? The split vent, right? Because we have a really low concentration of the analyte, so we don't have to do split injection. Now, so this is the function of the oven, as we discussed previously. Control uniform column temperature, right? And then column temperature slightly above the boiling. Okay, the in elution time of 2 to 30 minutes. Minimal temperatures give good resolution, but will decrease right? And the separation sorry. All right, we have two types: isothermal, fixed temperature during separation, the simple mixtures, and the second one is programmed temperature. The temperature is increased continuously or in steps as separation proceeds for sample of wide boiling range. Okay, remember. All right, in the HPLC, do you remember in HPLC we have how we control so that we have a better resolution of the analytes in the chromatogram, and better and we have to adjust better resolution, meaning that we need to separate the peaks, all right, clearly, and then we also need to shorten the elution time, right? How we do it? We control the mixture of the ratio of the mobile phase. What we call that term? Do you remember that? For the HPLC, how we control? Anybody remember?
Elution what?
What we have to do to control the resolution, isocratic and
Gradient.
we have to, right? Gradient, right? So isocratic is we use similar mixture of the mobile phase from the beginning until the end. Am I true? Am I correct? And what about the second one? So that the ratio of the mobile phase change, right? Through time. Am I true?
Yes.
So that purpose is similar for gas chromatography. We have isothermal, which is the temperature inside the oven is fixed from the beginning until the end of the analysis, and also we have programmed temperature, so that the temperature is increased continuously or in step, depend on how we program the temperature as separation proceeds. Okay, meaning that it's not similar temperature from the beginning until the end. It may be increased, all right, at certain time, and for how long depend on our program. It is for the same purpose, all right, to shorten the elution time. This is the difference between HPLC and GC on the step to have the better resolution, better separation, and also shorten the elution time. For HPLC, we have separation mode, isocratic or gradient elution, right? And for the GC, we have isothermal or programmed temperature. Remember, okay, why I stress on this too much? Maybe it might come in the form of questions in the final exam notes, right? So for simple samples, separation may be carried out under isothermal condition of constant temperature. For sample with wide range of volatility, meaning that in our sample we have a various type of analytes, right, that have different range of volatility, different boiling point. So we need to use temperature programming. Why? To enable the volatile compound to be resolved at low temperature and elution of later less volatile compounds to be speed up as the temperature increase. As I said, it is for similar purpose as the HPLC, to shorten the elution time. And second one is profile include a series of time events, initial isothermal period, pause at intermediate fixed temperature, different ramp rates, a final isothermal period, and automated cooling down of column to initial temperature at end of run, ready for the next cycle. This is oven temperature program, right? For example, initial temperature and then RAM. Okay. Right. We have to the temperature. This is temperature. All right. First we inject the sample. This is the temperature here, X, right? And then it RAM increase up to this temperature. Okay. Let's say Y, and then hold for how many seconds or minute, and then RAM again, increase again, X, Z temperature, right? And then maintain for long, and then cool down to X temperature, right? This is the example of the temperature. So this is how the isothermal and program temperature looks like for the chromatogram. For example, we have C8, C10, C12, C14, C16 here. For the isothermal separation of alkanes at 140 degree throughout, right? All the alkane species. And now, second one, B, is temperature program separation from 50 to 230 degree of Celsius at 4 degree Celsius per minute. This is the RAM speed for the temperature to increase, right? So we have here, okay, this is for the temperature program. So we have not so much elution time, right? For isothermal, we have to wait more than 20 minutes, right, to make sure that C16 appear. But for the temperature program, right, below 20 minutes, we already have C16 appear, right? So shorten the elution time, right? Understood? Understood, guys?
Doctor, can you repeat it?
Okay, I can repeat it. All right. Remember in HPLC, if we have compounds that come very late, okay, for the elution time, meaning that the compound, for example, for HPLC, this is a column, okay, and then we have the mobile phase, right? We can put the ratio of maybe what we have previously, hexane and water, okay, in ratio to 4. This is only for example, right? 1 to 2, and then if we use isocratic so the ratio of the hexane and H2O mobile phase similar from the beginning until end of the analysis. So then what happened, we have a very late because we have a compound that react strongly with the stationary phase and come very at a very long elution time. We have to wait a very long time to make sure that the peaks appear. So what happened in HPLC, we can program. All right, we have isocratic and gradient, so we can make a gradient elution. Meaning that the ratio of the mobile phase, okay, between hexane and H2O, not similar 1 to 2 ratio from beginning until end. We can program the instrument to increase, for example, the the hexane to be with ratio 2 to 1, okay, and so on, so that we can make sure that we don't have to wait for a really long time for the last peak to be appear, right? So that can be make it earlier. We can play with the mobile phase. Similar with the GC, rather than we use isothermal, okay, the similar temperature, right, from the beginning until end, we can use a temperature program. We can increase the temperature, decrease again, so that we can make sure that all the peaks appear for not a very long time. You see this is 20 minutes, right? After 20 minutes, maybe almost 30 minutes, then we have C16 appear. But when we program the temperature, before 20 minutes, we already have C16 appear, right? And the peak is also well distributed because we have programmed the temperature so that the separation is really nice, all right? Remember, you can see the C10 and C8, it is not separated well, right? Very close. When we program and distribute, you can separate C8 and C10 really nice. And we can we have to, you know, we don't have to wait for a longer time for C16 to appear because we have another analyte to appear, C18, C20, right? So we can program the temperature so that we can make it early. We don't have to wait for a long time, right? For the elution time. Below 20 minutes already we have C16. Excuse me. To make sure that the separation is well distributed, right? And the second one is to shorten the elution time. Okay, understood? So that in HPLC and GC both we have a technique on how to distribute the separation well and also to shorten the elution time. We can, for the HPLC, we can play with the mobile phase ratio, or we call as gradient elution. In the gas chromatography, we can play with the temperature program. We can play with temperature, all right, in the oven. We call as temperature program, right? In the HPLC, we have isocratic, meaning that we don't change anything. The ratio is from beginning until end is similar. And we have gradient elution, meaning that we can change with the ratio of the mobile phase. We can play with the ratio from the beginning until end. We can put anywhere we want the increment of the ratio or decrement of the ratio, so that we can have a really well distributed, really well separated peaks, and we can shorten the elution time. And in GC, we have isothermal, that we don't change anything. The temperature for the oven is similar from beginning until end, and we can have the second one. The temperature is being programmed so that we can separate the peaks of the analytes well, right? Not really close like this, and also we can shorten the elution time, right? Understood?
Yes, sir.
All right, normally this type of question is asked in the final exam, right? Right, now we see the temperature effect on the retention. All right. This is 75 degrees. Okay, we can see C8 and then the C10, C11, right? C12, right? This one we have to wait longer, right? And for 110, of course, we don't have to wait longer time. This is 20 minutes. This is only 10 minutes, but we can get until C12. But the separation is really bad. You can see that. Really bad separation, right? Really close to each other. And we can increase more so that we don't need to wait for a long time for the separation, or for the elution time. We can have C12 lower than 6 minutes, right? But the separation is really, really bad, right? You cannot differentiate which one is C10 or C8. It's really close to each other. So this is why we need to do the temperature program, so that at we can have the 75 degrees of Celsius up to what is C11, right? Up to 60 minutes, and then we can increase the temperature up to 110, okay, so that the peak the peak of C12 appear early. We don't need to have to wait for a long time. Okay, and we can also shorten the elution time between C10 and C11, C8 and C10. Right, can play with the temperature. Right, understood? The reason why we need to do program temperature or temperature program, because if you have a lot of analytes, we need to do a good separation, okay, and then we don't have, we play with the time, we shorten the elution time, right? So that we don't have to wait longer, right? So just set the temperature. Of course, we need to know our analyte first, right? That's why we have to do screening first, right? Oh, this is the analyte. Okay. So if you have a bad chromatogram, a really close, really long time, then so that we, after we do a first analysis, and then we do the second one with a, a temperature program, so that we have a good separation. We have all peaks appeared in a really not so long time. Okay. GC columns and stationary phase. The heart of the GC system where the separation occurs, of course, the column. So determines efficiency and selectivity. Okay, we have as we seen in the video, we have two type of column, pack and capillary, or open tubular column, right? We have a silica column for polyamide layer and liquid phase layer inside there. It's liquid phase, right? All right, porous layer open tubular column or plot. Okay, okay, we can see in the electron scanning image, this is how the porous layer looks like. Okay, and we have a well coated open tubular column. We don't have this like a porous thing here. We have a really clear, clear coat inside the column. Column looks like full with or packed with the solid material inside. So open tubular column plot or WCOT. Okay. We have no support material, flexible fused silica coated with polyamide layer. The temperature is for lower than 350 degree or else coating pyrolyzed. Okay, meaning that if we use a higher temperature, the coating itself will be burned. Okay, and then the what is ID inside? Diameter is 0.1 millimeter to 0.75 millimeter. The film thickness is 0.1 to 5 micrometer. The column length from 5 to 50 meter, really long, right? But this is really, thin, so with that we can make it in the form of coil, put inside the oven. So as ID and film thickness sample increase and sample capacity increase, the efficiency is decreased. So this is the formula. As the internal diameter and film thickness increase, right? This one and this one, the sample capacity also increase and C is decrease, right? Typically, analytical column is 25 meter long with a 0.22 millimeter internal diameter and 0.25 micrometer of film thickness. That is typical. Consists of three main components: a column tubing, a support material, and liquid stationary phase. And column tubing criteria is inert, thermally stable, and coil up. The type of the tubing is copper, stainless steel, or glass. And typical size of 1 to 3 meter long. And what is that? The outside diameter, right? 1 to 16, 1 over 16, 1 over 8, and 1 over 4 inch, right? With 2 to 3 millimeter internal diameter. So inner surface silated to reduce interaction with polar analytes. So we now compare the packed and open tubular column or the capillary column. All right, for the efficiency, the packed column is low to moderate, meaning that the efficiency is really, we want the high efficiency, right? So that why we use open tubular. Sensitivity also low, and that is why the packed column is no longer used, or really, rarely used in the gas chromatography, because in the analysis we need to have the efficiency and sensitivity. That is a really important thing in the analysis. We have to be efficient and sensitive. Meaning that, what is sensitive? Meaning that our instrument can detect the analytes even with low concentration. That is sensitive. If you have a sensitive friend, right? Salah cakap sikit merajuk, right? If you have a sensitive friend who always, emotional, right? If something really small thing happens, it triggers their emotion, right? So that is how sensitive of instrument. Meaning that if we have a perempuan neural, betul ke ni girls? Is it true that a woman sensitive man? So that you say that packed column are women? No, Ani cakap, Sabina cakap Irfan lah tu. Alright. That's the example, alright. But in instrument, we need to have a sensitive instrument, okay? If we have an instrument like Irfan, where Irfan is not sensitive at all, so the instrument will be useless. So we need to have a sensitive instrument. It's okay to have a sensitive instrument. It's really good, right? The operation, of course, for the packed column is easy rather than the open tubular column, less easy. Not so difficult, right? And the sample amount, we can put a large amount of sample, or in other words, the packed column need to have a really large amount of sample. That is not so good actually. The good instrument only need to put a small amount of sample, right? And the price, of course, the packed column are more cheaper than the open tubular column. It's really expensive, but in the analysis, as I said, that the purpose of analysis is to have the efficiency, sensitivity, and also we need to, we need the instrument that only require a small amount of sample. So here, the winner is open tubular column, right? Yeah. See, you watch the video, it said that the packed column is no longer used widely, right? So type of stationary phase in open tubular column, WCOT or PCOT, is non-polar column, separation according to analyte volatility, increase with boiling point, retention increases with the chain length. The polar column, separation according to volatility as not, and also to polarity for polar analyte, more highly retained compared to non-polar of similar volatility. We have a similar volatility of analyte, so which one will retain longer of analyte, because we have a polar column. Remember, polar love polar, right? And remember also, polar mean by charge, right? Charge is negative will attract to positive, and positive will attract to negative. But the polarity is the whole molecule, meaning that if we have a unbalanced charge of analyte, it will or attract to the also unbalanced charge of the analyte, meaning that we have positive and negative. the molecule of the polar analyte have positive and negative charge, so it will attract each other. All right. So bonding or dipoles also occur in the polar columns. Elution can change between type if analyte is a mixture, have different group, right? So order of elution, if the analyte in the mixture have different functional group. For the non-polar stationary phase, the hydrocarbons, packed column only, we have the epizone L, squalane, or dimethyl polysiloxane, okay, DPMS, for open tubular. Product available is just SGE, BP1, Agilent. We watched the Agilent video, right? So we have a different brand of the non-polar stationary phase. And phenyl methyl polysiloxane for open tubular tube, we have Agilent HP5, right? So polar stationary phase, a substitute silicon, a good temperature stability, right? For example, is trifluoropropyl. Product available are Agilent VF200S and Restec RTX200. So ideally suit for analysis of ketones, aldehydes, nitro or chloro containing compounds. HS is polyaromatic hydrocarbons, right? And unsaturated compounds, silanes, and CFCS. What is CFCS? Like this one, right? All right, this is the example of the food analysis. Okay, this is the chromatogram. The column used is 25 meter long with the 0.22 millimeter ID and 0.25 micrometer. What? This is what? If you have this is ID, what is this? Thickness. Measurement. Film thickness. All right. Okay, you can just read this. This is only the example of the column that we have available in the market. For the specialized column phase, so first one we have a column for acid, right? If we have acidic type of sample, so this is the type of columns that we need to have. And we also have a column for base and chiral columns, which is substitute a cyclodextrin bonded to open tubular column. So remember, a different type of analyte requires a different type of column, right? So how we need to know this? So we can refer the standard method. Okay, if you need to analyze something, refer to the standard method. What is the procedure, type of column, and so on available there. Of course, according to the type of the analyte, to avoid any damage in the column. Acidic sample with a not suitable column, if we damage the column, we need to use a suitable one, and then also we need to increase the sensitivity as well as the selectivity. This is the column type and how it separate. Okay, for example, this one, we have the methanol, ethanol, propanol, acetone, and 1-propanol. This is where we use packed column. So this is So this is how it's separate, and then This is an open tubular column, right? Right, we can have more separation only with the shortened elution time. Okay, this one is about 10 minutes. It's about the temperature program. Okay. Right. You see on non-polar WCOT, right? Ultra 100% dimethyl polysiloxane, right? This is the this is the dimension of the column, right? You can see this for 70 minutes. 70 minutes for all the carbon change for the hydrocarbons to be appeared. Carbowax 20-meter column, polyethylene glycol type with the quite similar dimension. Okay, a similar temperature program, but we can see that it can shorten the elution time. Okay, lower than the carbon change up to C20 appear there. So this is the effect of the stationary phase type. Okay, for example, polar and non-polar. This is the non-polar is dimethyl polysiloxane or DP. Okay, 100% methyl. Okay, and then this one is polar. Okay, wax. Okay, polyethylene glycol base. Okay, so what is the difference between the chromatogram? What is the difference? We can see the separation here is not so good, right? But here, okay, here the peaks are here, 1 and 2, but now it's separated. Greater length gives greater efficiency and resolution, but retention times are longer and assays are slower. This is for 15 meters of column length, 30 meters, and 60 meters. Okay. So of a column inside diameter, narrow columns give retention times but reduce sample loadability and more injection problems. Okay, this one is 0.1 millimeter internal diameter. This one is 0.25 millimeter internal diameter. Right, R is 4 and this one R is 1.63. R represent the what we call that? What we call this? The distance between two peaks, right? So narrow efficiency. Which one is narrow? Which one is narrow? First one, second one. Why this one is narrow? Is that according to the inside diameter? Why you say that this one is narrow?
The up one, narrow.
how we measure the inside diameter. Narrow column give increased efficiency and reduce retention time. Okay, in that this one is narrow, but how we measure the diameter? To where? To here. Diameter. Slides of the columns. So how to measure the inside diameter?
The small circles.
Which one is inside diameter?
Liquid phase layer.
Which one? Column. And the second one is the open tubular column. So which one is inside diameter? This is outside diameter, right? So inside diameter is where? From here to here. Am I correct? So what happens if inside diameter is small?
Increase efficiency.
Film thickness is here. The film thickness. So which one is the inside diameter? This one. So which one is the inside diameter? From here to here. So what happened? The column, we go to the slide that I've shown you. Okay. It said that narrow columns give increased efficiency. What means by narrow columns? Between 0.1 millimeter in diameter and 0.25 millimeter internal diameter.
0.1.
Really? No, how we say that? First thing is how you describe narrow. So
Small.
which one is more efficient? Meaning that lower retention time and also efficient. Chromatogram, which one is more efficient? So the R between 4 and 3, which one is better? What is the good value of R? Back to the theory. Please. Which one is better for R value? Okay, now we look at the effect of the coating thickness. Greater film thickness, a more liquid phase, give increased retention. Increase retention times and increase loadability, but reduce efficiency. Okay, this one is the thickness is 0.25 micrometer. Okay, the R for 0.5 micrometer, the R is 3.6, and this one is 1 micrometer, and the R is 4.96. Okay, greater film thickness give increased retention time and increase loadability, but reduce efficiency. Right, we see here. The greater film thickness, okay, increase the retention time. Okay, for here we only have to wait for 4.7 minutes for the peaks to be appear, but for 0.5 we need to wait until 7.4, and from 1 micrometer we need to have up to 13.2 minutes for this peak to be appear. And what about the R? (3.14, 3.6, and 4.69). Okay. Anybody can comment on the R value? What happens if we increase the film thickness inside the column? Anybody? Say that. R larger than 1.5. Okay, meaning that we look again to the, so between 4 and 1.3, which one is better? Four, right? Okay, but the retention time is decreased when we use narrow columns. Okay, but the R is not so good, right? The separation efficiency is not so good because the peak are close, really close. We need to separate well, right, to differentiate the peaks. right? Here, column inside diameter. Anybody can answer me. What is mean by narrow? How to calculate the inside diameter? From this one and this one, which one is narrow? Of course, 0.1 is narrow. How to calculate the column inside diameter is from here to here, right? The narrow column gives increased efficiency 4, right? But reduce sample loadability and more injection problem, right? Am I true? Correct me if I'm wrong. We are learning. Guys, are you there? So narrow is what? Large inside diameter. So how? Okay, if I have this one, the across of the column, and this one, which one is narrow? A or B?
B.
Why we call this B narrow? That's why I asked what this mean by narrow. What is mean by narrow? You said B. So am I true that in here to here, am I true?
Yes.
All right. Okay, so what is mean by narrow? Why we call it B is narrow? You said that B is narrow, right? So why? So between 0.1 and 0.25, which one is narrow? Again, okay, 0.1. So from between A and B, which one is narrow? If you said that 0.1 is narrow,
B is narrow, 0.25 is narrow.
B is narrow, 0.25 is narrow. Who said that? Anis? Who?
Anis.
Okay, how? Why you say that 0.25 is narrow?
Because the large inside diameter. So the column is
Large inside diameter meaning that the column is narrow. So what is mean by narrow? Maybe some question they don't give the value of the inside diameter, but they give the word narrow or what. So what is mean by narrow? You can Google it or do anything to describe what is mean by narrow columns. Thickness, we are now talking about ID, not about the diameter. column. Here we talk about the inside diameter. And here we talk about the film. This is layer thickness, right? So which one is inside diameter? From here to here. Am I true?
Yes.
So which one is narrow? Back to the question. Or high is narrow? Is narrow.
High ID.
Why high ID is narrow? Again, this. What mean by narrow? You can say it in Malay.
Kecil.
What is kecil? What is small about the column? We are talking about inside diameter, right? What is small? Why you say that ID is narrow? Anybody say that low ID is narrow?
Large ID will make the column smaller.
Large ID will make the column smaller. Meaning that large measurement between here and here will make the column smaller.
Yes.
How it be small? For example, this is 0.25 and we have the another one is here is 0.1. So this column is smaller.
Yes.
Why you say that this column is smaller than this column?
The distance between the inside diameter and outside diameter is smaller.
Distance between
Inside diameter and outside diameter is smaller.
distance between this one and this one.
The smallest one. Yes, dekat tengah-tengah.
That this one considered as narrow rather than this one.
Yeah.
Okay. Meaning that this one is narrow, and this one is not narrow. You can share if you have any email to share. Yes.
Rika, bukan kalau ID tu makin kecil, so dalam situ akan jadi lebih narrow.
Yes. Who's that speaking? Ifan?
Ni.
In that?
So 0.9 tu adalah narrow.
0.1 is narrow. Right?
0.1
Okay.
is narrow.
Yes. That's why I'm keep asking you, what is narrow means? Find the definition of narrow. What is mean by narrow?
Okay.
All right. Sempit, right? So between this one and this one, which one is narrow? A and B.
The second one.
B. This one is narrow. This one is narrow, right?
Yes.
Okay, so the problem is with this image. Often, this one is already true. 0.1 is narrow. Efficiency is increased 4 and reduce retention time. Okay. And this one is not narrow, but maybe the example is not so good, right? Maybe the example is not so good because this peak should become early actually. Okay. And the sample loadability and more injection problem. What is mean by sample loadability and injection problem? Guys, just imagine we have a really small. Is it require a small amount of energy or large amount of energy to inject your sample inside a very narrow column? Need to push it really hard within column. Okay, when you come to UTM, I will show you how hard it is to inject in a really narrow column because our sample full of analytes, you know, berhimpit squeeze themselves to be inside the column. That's why we have a problem in sample loadability and more injection problem. Okay, rather than the large ID column, it's really easy to inject the sample. All right. Of course, we have a good efficiency and a good retention time with the narrow column. But again, the problem is with the loadability and injection of the sample. So we have an optimal need to push really hard in the injection of sample, and then the retention time and efficiency is also good. Sorry, I spent a lot of time there because I need for you to understand which one is narrow, which one is not narrow. Okay, and this one is about the coating thickness. You can imagine this because it is about the of the coating inside the column. So which one is better? Greater film thickness, more liquid phase inside, give increased retention time and increased loadability, but reduce efficiency. If we have a really thick film inside the column, also we have a problem to inject the sample. It also become narrow. Okay, meaning that retention time is increased because there's an interaction, a lot of interaction between analytes and the stationary phase, right? And increase the retention time because they like to talk to each other inside the column between the analytes and the stationary phase. The the film thick, the thick film inside the column. So they interact together, banyak berbual dalam. So it need a lot of much higher retention time rather than not so thick a film thick inside the column, and also reduce. Okay, so we don't need to have a really thick liquid phase, okay, for the stationary phase inside the column. Okay, a non-selective detector responds to all compound except the carrier gas. Of course, we don't need to have a response for the carrier gas. It is only the mobile phase. Selective detector responds to a range of compounds with a common physical or chemical property. A specific detector responds to a single chemical. We have various type of detector. Normally, a flame ionization detector, a thermal conductivity detector, electron capture detector, nitrogen phosphorus, flame photometric detector, photo ionization detector, and so on. Normally, we have this one, FID and PID, right? For the flame ionization, compound are burned in a hydrogen air flame. A carbon-containing compound produce ions that are attracted to the collector. The number of ions hitting the collector is measured, and a signal is generated. Okay, so after being, if you watch the video, after being introduced into the, after being separated, the analytes will introduce into the flame, and then it will be ionized, and it will be attracted to the different type of it will be attracted to the opposite charge of the negative to the positive and positive to the negative, and the signal is generated, right? For the selectivity, compound with CH bonds, okay, hydrocarbons, sensitivity is 0.1 to 10 nanogram. The linear range is there with the combustion gas, hydrogen and air. You make up helium or nitrogen, temperature range. You can read all this. You know the concept of the flame ionization already, right? We have also thermal conductivity. The cell contains a heated filament with an applied current. A carrier gas containing a solute passes through the cell. In the filament current occurs. The current change is compared against the reference cell. The reference is the difference is measured and generated. So this is how the detector of the TCD detector function. It is for the selectivity is for all compound except for the carrier gas. Okay, it's a universal one. Supplied from a nickel foil lining detector cell. Current is generated in the cell. Electronegative compound capture electrons, resulting in a reduction in the current. The amount of a current loss is indirectly measured, and a signal is generated. So the measurement is based on the current, right? Because the first one, electron is being supplied. So if the electronegative compound captured electrons, resulting in a reduction in the current, the amount of the current loss is measured and then generated as a signal. Selectivity for halogens, nitrates, and conjugated carbonyls. Also, we have MS. Of course, we have GCMS. So we have, of course, in the mass spectrometry, we have chromatography, and then ionization, okay, ion source, and we sort the mass by mass analyzer. Okay, the ions will be sorted by mass, and then detection is using the ion detector, and we have the mass spectrum will be in the form of. So the mechanism, once the components leave the GC column, they are ionized by the mass spectrometer electron or chemical annihilation source. The ionized molecule are then accelerated through the instrument mass analyzer, for example, quadrupole or trap analyzer. And it is here that ions are separated based on their different mass to charge ratio. Okay, and then the selectivity for halogen nitrate and conjugated carbonyls. This one is also commonly used in the industries in the R&D institutions. Of course, in them also we have GCMS. Here, which type of the detector that we need to use for different type of species, and for the linear range selectivity and so on, you can refer this table. All right, for the class activity, I have already distributed all of it to groups, right? Since the beginning of the class, okay? Can you suggest the best injector for these compounds? 1, 2, 3, 4. Is it there in your note?
Yes.
So that's your activity based on group. So I will put the a section in the e-learning for you to submit in the form of PDF. Okay. So application of GC, a lot of application of GC, as I said, for petrochemical, environmental, organic pollutants, forensic, pharmaceuticals, biology, cosmetics, food, so on. So GCMS separation of toxic substance in, for example. So we have detect ethylene glycol there in the toothpaste. Polychlorinated biphenyl, PCB, right? The toxic compounds. Explosives can analyze explosives using GC ECD. Identification of Staphylococcus aureus in food. This is a type of bacteria. Also, we can detect using GCMS. Of course, we have the library for the mass to charge ratio of the Staphylococcus, so that we can compare with our sample. Right. So if you have question, please ask me. If you don't want to ask now, please ask in the WhatsApp group. And remember to do your assignment based on your group. In your group, submit it in the e-learning for this. That's the best detector of these compounds. All right. For this. Oh, sorry. The answer that being given to you in your notes. In your notes, is there any answer there already there? There is already. Okay. Just we discuss here. So kalau dah ada jawapan, okay, if there is only the answer there, so just you need to know that this type of true, you have the answer already.
Yes.
Okay, so this one, right? So referring to the table, the first compound need to use FID. Here, universal to carbon change, right? Number 2, we need to use ECD Why ECD? Because electronegative group such as halogens, oxygen containing groups. All right, so we need to use ECD. So number 3, FID, also because it is a normal carbon change. Number 4, TCD, natural gas containing alkanes, H2S and propyl mercaptan. Okay, TCD. Why TCD is universal and term conductivity and respond characteristic in terms of the concentration. And number 5, we use ECD. Why? Because ECD is suitable. Where is ECD? For electronegative compounds such as halogen. We have is halogen. So if we have halogens, normally we use ECD for detection. All right. Okay, that's all for today. I also record this session and I will upload in the e-learning as usual. So for the next class, we will learn about sample preparation and sample analysis using a chromatography technique for the chromatography technique. Right, if you don't have any questions, so that's all. Thank you and Assalamualaikum.
Thank you, Doctor.
Thank you, Doctor.
Yes, thank you. Okay, welcome. Welcome.
Thank you, Doctor.